So if soils contain, out of the total amount of phosphorus present, 50% as organic phosphorus, and if the total phosphorus is, oh my gosh, it could be in the low thousands. It could be in the high hundreds. Let's say that it's 1,000, and 50% of that's organic phosphorus, which is 500 parts per million. And plants, depending on how you manage phosphorus, might only need maybe 10 to 20 parts per million in the soluble phase over a growing season. So if you have 500 parts per million phosphorus in the organic form, how do plants eventually see this? Plants eventually will, quote, see this phosphorus via a process called mineralization. And the process of mineralization is identical, well, with respect to definition, as you learned in the nitrogen unit, or if you learned in nitrogen units in the past. And simply put, mineralization of organic P is the conversion of organic phosphorus to inorganic phosphorus. And this is how this works. It's catalyzed by something called the phosphatase enzyme. The phosphatase enzyme is present in acidic soils, and a different form is present in alkaline soils, but they operate the same. And their role in soils is to cleave orthophosphate from a functional group, from an organic group, right? So this reaction shows you how this works. R is an organic functional group, doesn't matter what it is, and it has orthophosphate stuck or sticking out off the edge. You need water for this to occur. This is an enzyme-driven response to a lack of phosphate in the soil. In the presence of phosphatase enzyme, the orthophosphate is cleaved and the orthophosphate is replaced with OH, right? And here's H over here. So what this tells you, this is HPO4, 2 minus. And this reaction is actually a hydrolysis reaction, right? It's the splitting of water. This occurs via the phosphatase enzyme. The phosphatase enzyme, you don't need to know this for this class, but the phosphatase enzyme can be exuded by microorganisms if they perceive a deficiency of phosphorus. And the phosphatase enzyme can be exuded by plant roots if the plant perceives a deficiency. So another means by which plants can overcome P deficiency symptoms in soils. So it's not on this slide, but the reaction can go from right to left, and that would be immobilization. Immobilization occurs when microorganisms feel a phosphorus deficiency, and when their populations are exploding because perhaps you added an energy source in the form of carbon or an amendment that did not contain a lot of phosphorus. Where are the microorganisms going to obtain that phosphorus? They're going to obtain that phosphorus from orthophosphates found in the soil solution phase. So that's immobilization. Whereas mineralization is the release of organic phosphorus to inorganic phosphorus in the form of orthophosphate, like you see in this picture. When we talked about mineralization and immobilization in the nitrogen unit, we used ratios of 20 to 1 or less, where mineralization occurs, and 30 to 1 or greater, where immobilization occurs with respect to the carbon to nitrogen ratio. The nice part about mineralization and immobilization with respect to phosphorus is those numbers are almost identical to the nitrogen unit, except you just multiply by 10. Okay, so the balance between mineralization and immobilization is this for the carbon to phosphorus ratio in soils. If you're less than 200 to 1, you see mineralization dominating. If you're greater than 300 to 1, you have immobilization dominating. And if you're somewhere in between, they basically cancel each other out. Cancel each other out. Out. All right. So hopefully that makes sense to you. We're going to leave this here, keep it rather simple.